Hi there and welcome. My name is James Leach, and this video will explore MCAT hydrostatics. This review is going to cover Pascal's principle, or the transmission of pressure within an ideal fluid, Archimedes Principle and how it relates to buoyancy, and finally cohesion and adhesion, which affect the behavior of the surface of a liquid. In this video, we'll be working towards recognizing and predicting how static fluids behave under a variety of conditions and identifying the properties which cause these phenomena. This will allow you to answer questions such as this, which requires some calculation legwork, as well as the more conceptual applications of hydrostatics. The first concept to be elucidated is Pascal's principle. This principle only holds true for ideal fluids, those that are incompressible, and it tells us that a change in pressure will be transmitted undiminished throughout the fluid and to the walls of the container. A common example is the hydraulic lift, which depends upon energy and pressure being transmitted through the fluid undiminished in order to do work. Let's make sense of that by sorting out what all these arrows and letters mean. The point of the hydraulic lift is to generate mechanical advantage, or more simply, to be able to lift up something heavy which we could not otherwise lift by taking advantage of the incompressibility of ideal fluids. If a force is applied to the small piston on the left of this lift, it exerts a pressure on the fluid equal to force per unit area. Remembering that pressure is transmitted undiminished throughout an ideal fluid, that same pressure must be exerted on the larger piston on the right of your screen, which is also expressed as force per unit area. Given that the cross-sectional area on the left piston is less than the cross-sectional area of the right piston, we find that the force exerted on the right piston must also be greater. How can we make sense of a small force generating a larger force seemingly out of nowhere? To complete our understanding, let's look at the displacement of the pistons. The force applied to the left piston must be exerted over a greater distance than the force applied to the larger right piston. That is, the displacement of piston 1 is greater than the displacement of piston 2. This ties into two very important points about Pascal's principle. Firstly, it gives us the expression for the conservation of volume, or the incompressibility of the fluid. The volume of the fluid moved by the first piston is equal to the volume of fluid filling the space vacated by that second piston. Or, in other words, the amount of fluid that moves the second piston. Secondly, because ideal fluids are frictionless systems, energy is also conserved. This helps to explain how a small force at one point can generate a larger force at another if applied over a greater distance. For this, we're going to look to our good old understanding of work, which equals pressure times the volume of the fluid displaced. We know that pressure equals force per unit area, and the volume of fluid being moved equals the area of the piston times the distance it moves. So let's just sub those expressions from the top of the page into this work formula to see the conservation of work, or energy, according to Pascal's principle. The force on piston 1 times the distance it moves must equal the force on piston 2 times the distance it is moved. Practically then, this says that if you apply a small force to that small piston over a great distance, you can generate enough mechanical advantage to exert a large force to a large surface over a short distance. Using hydraulic lifts, mechanics lift cars they can't otherwise lift with their bare hands by applying small forces over great distances, thereby lifting heavy cars short distances. Let's shift gears now and delve into the findings of another legendary physicist, Archimedes. We'll skip the old story about the crown and the bathtub and look instead at something a little more practical these days, this large ship. The reason it is not sinking is because it is being buoyed up by the buoyant force. What Archimedes observed was that the volume of fluid displaced by an object, in this case the ship, is equal to the volume of the ship that is submerged. The mass of that displaced fluid exerts a force against the ship. That force is equal to the mass of fluid displaced times the acceleration of that fluid, which is just the acceleration due to gravity. In mathematical terms, the buoyant force, which always points upwards or against gravity, is equal to the density of the fluid times the volume of the object that is beneath the surface of the fluid, which, taken together, just gives us the mass of the displaced fluid. That mass, multiplied by the acceleration due to gravity, gives us the buoyant force. An important note here. Buoyant force depends upon the density of the fluid, not the density of the object. Be prepared for the MCAT to give you both and expect you to know which one to apply. Speaking of application, let's take our knowledge of Archimedes' principle and apply it to determining how and why objects sink or float. This bowling ball, as you are probably aware, will have the tendency to sink in water. That means that the ball will accelerate downwards when placed in water. Perhaps you recall from Newtonian mechanics, if the ball is accelerating downwards, there must be a net downwards force. Our two forces here are the downwards pointing force of gravity and the upwards pointing buoyant force. If the net force points down, then the force of gravity must be greater than the buoyant force. Extrapolating from that, we'll sub in the density of the ball times the volume of the ball to get mass, and multiply that by acceleration to find the force of gravity. And then we'll sub in our terms for buoyant force. Eliminating like terms, we come to the final determination of whether something will float in a given substance, whether it is more or less dense than the substance. Since the buoyant force is less than the gravitational force, we know that this bowling ball is more dense than water and will therefore sink in water. Things get slightly more complicated when it comes to objects like this apple, which tend to float in water. If the object is floating, it is in equilibrium with no net force accelerating it in any direction, or the buoyant force is equal to the gravitational force. Subbing in the same terms for gravitational force and buoyant force as before, we can cancel out the like terms for gravity and rearrange to see that the ratio of the density of the apple to the density of the water is equal to the ratio of the volume of the apple submerged to its total volume. Put differently, the percentage of that apple that is submerged is equal to its specific gravity. Let's shift gears again into our last topic for this video, cohesion and adhesion. In any liquid, a molecule resting in the middle of that liquid experiences equal attractive forces on all sides because it is surrounded by identical molecules. As such, that molecule is in equilibrium and is not being pulled in any direction. But let's look at a molecule on the surface of this liquid. These surface molecules are feeling greater attractive forces from the other liquid molecules than from the air above them. The net force pulls them towards the center of the liquid. Adhesion occurs due to the opposite scenario, where molecules in the liquid are more attracted to the surface of their container than to the other molecules in the liquid. This phenomenon serves to explain why we see a concave meniscus form in test tubes. Water molecules are more attracted to the surface of the test tube than to other molecules. Thus, we see the concave surface due to the water molecules maximizing their contact with the surface of the test tube. Now it's time to apply the concepts from this video to a set of MCAT-style problems. This first question, the one from the beginning of the video, is an opportunity to apply your understanding of buoyancy and Archimedes Principle, keeping in mind that apparent weight is the net downward force on an object in a liquid. The first clue here is that the object is sinking, so the force of gravity is greater than the buoyant force. The magnitude of this difference is given by the apparent weight, so the force of gravity minus the buoyant force equals 16 newtons. Subbing in those terms for the force of gravity and the buoyant force from earlier in the video, which are just new ways of saying force equals mass times acceleration, we come up with this expression. Those are the two key steps in solving this problem. The rest is just plug and chug, so let's see where all the numbers come from. The volume of the object is 5 meters cubed, and g, of course, equals 10 meters per second squared. The density of water is 1,000 kilograms per meter cubed. Here, we'll just repeat the values for the volume of the object submerged and for gravity, and we still have our net force of 16 newtons. Let's multiply those group terms together to make our lives a little bit easier here. Then, rearranging our terms, we end up with this. A number slightly over 5,000 divided by 50 is going to equal some number slightly over 1,000. This aligns nicely with choice B. Now apply your knowledge of cohesion and adhesion to this problem. When there is a concave meniscus, the liquid molecules are more attracted to the walls of the container than to the other liquid molecules. In a convex meniscus, then, the liquid molecules are minimizing their contact with the surface of the test tube, meaning that the cohesive forces must be greater than the adhesive forces in this substance. This last question tests your knowledge of Pascal's principle. Give it a shot. The first problem you may have noticed here is that if a frictional force is acting, which must by definition be non-conservative, then energy is not being conserved in this system. Applying Pascal's principle depends upon the conservation of energy. However, it doesn't seem, on the surface at least, entirely unreasonable to just subtract the amount of frictional force, since it is given to us, from the weight of the car, as is done in answer choice A. On closer inspection, however, The friction force is given as newtons per meter squared. We don't know the dimensions of this container, so we don't know how many newtons of frictional force are exerted on the fluid. Thus, more information would be required in order to make this determination. In this video, we analyze how mechanical advantage can be generated via the use of incompressible fluids by applying Pascal's principle to the hydraulic lift. We derive the buoyant force from Archimedes' observation that the fluid displaced by an object exerts a force equal to its weight on the object itself. This tied neatly into buoyancy, where the important relationships we deduced were that objects float when the force of gravity is equal to the buoyant force, and they sink when the force of gravity is greater than the buoyant force. We also differentiated between cohesion and adhesion. Cohesion is the attraction felt between molecules within a liquid for one another, while adhesion, on the other hand, is the attraction of those molecules to something outside the liquid. Thanks for watching this hydrostatics review. It was an intense overview of some MCAT fluids. Good luck applying all those concepts throughout your studying and, of course, on test day.